Hi, everyone. Welcome to Math 70. This video lecture is on section 4.4, rules for exponents. So just as a brief reminder, an exponent is a compact way of writing repeated multiplication. Exponentials are repeated multiplication, and we're going to come back to this multiplication. We're going to come back to this fact again and again as we develop our rules for exponents. The 3 is called the base. The 4 is called the exponent or the power. Exponents are repeated multiplication. Let's take a look at that. Let's do 3 to the 4th times 3 to the 5th. Well, since exponents are repeated multiplication, I can just write out all of that repeated multiplication. I have 1, 2, 3, 4 threes multiplied together. And then 1, 2, 3, 4, 5 threes multiplied together. All told, I have 9 of them. 4, 5, 6, 7, 8, 9. 3 to the 9th. And notice that 4 plus 5 equals 9. You add powers. 3 to the 4th times 3 to the 5th. I can write as 3 to the 4 plus 5 up in the power, which gives me 3 to the 9th. And that's our first rule. Multiplying exponential terms with the same base, and that's important. I needed it to be 3 as the base both times. You add the powers or add the exponents. Moving right along, I'm just going to give you a list of these with a short example for each, because there are quite a lot of rules of exponents, and every single one of them comes from the fact that exponential notation is repeated multiplication. Let's look at 3 to the 7th, and now I'm going to divide it by 3 squared. Well, since exponential notation is repeated multiplication, I can write out the multiplications on the top and the bottom. There's 3 multiplied by itself 7 times on the top, and 3 multiplied by itself twice on the bottom. And now I cancel some of the 3's. Cancel that 3 and cancel that 3, because when we divide, we get to cancel. And what do I have? I have 1, 2, 3, 4, 5 left. And that just happens to be what I get when I subtract 7 minus 2. So we subtract the powers. Let's see, dividing exponentials with the same base, you subtract the bottom power from the top power. Four to the 8 divided by 4 squared is 4 to the 8 minus 2, which is 4 to the 6th. And that's our second rule. I'll try to keep track and number all of them. Multiplying exponential terms with the same base, you add the powers. dividing exponentials with the same base, you subtract the bottom power from the top power. Okay, let's get our next rule. What about, let's look at 3 to the 7th divided by 3 to the 7th. Well, I'm going to do this in two ways. First, any number divided by itself is 1. And if I want to be really clear, I'll write out all my 3's. And then I cancel all of them and I get 1. 3 to the 7th divided by 3 to the 7th is 1. But let's use rule 2, which is subtract the powers. 3 to the 7th divided by 3 to the 7th, I should subtract the bottom power from the top power, and that's 3 to the 0, and I already said that equals 1. So 3 to the 0 equals 1. So that's our next rule. Any number raised to the 0 power equals 1. 2 to the 0 equals 1. 19 to the 0 equals 1. 1/3 to the 0, that also equals 1. Any number raised to the 0 power equals 1. Basically, with these rules, and you should copy all these rules down into your own notes so that you have a chance to write those rules by hand. With these rules, you just have to start practicing them and using them and checking your work, and that's what your homework is for, so you can check that you're using the rules correctly. And you just have to practice the rules until you get them right almost all the time. Next rule. I can do this rule in two different ways as well. Let's look at 1/3 to the 4th. Well, that's 1 divided by 3 times 3 times 3 times 3. Again, we're going to use rule 3 and rewrite the 1 as 3 to the 0. That's what I just said. 3 to the 0 equals 1, so I can rewrite the 1 in the numerator as 3 to the 0. And I have these 4 3's in the bottom. So rewriting 1/3 to the 4th as 3 to the 0 over 3 to the 4, that's the power. Now I'm going to use rule 2 and write that as 3 to the 0 minus 4. 0 minus 4 is -4. So what I end up with is that 1/3 to the 4th equals 3 to the minus 4. So if there is an exponential in the denominator, you can move it to the numerator and change the sign, change of the power. So if I have 1/2 to the 7th, I can write that as 2 to the minus 7. If I have 1/5 cubed, or to the 3rd power, I can write that as 5 to the minus 3. Now, this rule works even if the power is negative. By the way, notice negative powers are allowed. They just represent division. So let's explore that a little bit more. Let's look at the 1 over 2 to the 7, which is 2 to the minus 7. Now let's look at 4 to the minus 3. Well, this is in the numerator, and so I can move it to the denominator and make the power positive. So rule 4 is here. If there's an exponential in the denominator, you can move it to the numerator and change the sign of the power. This is also rule 4. You can also move exponentials into the denominator by changing the sign of the power. It's just, this is a very flexible rule. If I have 1 over 2 to the minus 3, I can move it up into the numerator and change the sign of the power. 1 over 2 to the minus 3 is the same as 2 cubed. And if I have, let's say 4 to the 5th, I can move it down into the denominator and just change the sign again. So you can rewrite your exponentials a lot of different ways just by changing the sign and moving where it belongs, moving it up or down into the numerator or the denominator. Here's a nice consequence of rule 4. One over 3 equals 3 to the minus 1. Because 3 to the 1, well, that's just 3 with no extra multiplication going on. So then I move it down into the denominator. Well, that was a little confusing. Let's stop there. 3 to the 1 equals 3. So if I have 1 over 3, that's like 1 over 3 to the first. And now I can move it up to the numerator and make it a 3 to the minus 1. In general, 1 over any variable I can rewrite as that variable to the negative first power. This is very common. Switching between a fraction form and an exponential form with variables is super common. All right, quick review. These aren't real new rules. I'm just going to review all 4 of these really fast before we move on to some other similar rules that also come from repeated multiplication. So same base multiplied with different powers. I add the powers. Oops, that's a 7. And I get 3 to the 9. Same base. Divide the exponentials. I subtract the powers. And that gives me that any number a to the 0 is 1 for any a. It gives me that 1 over any number. I can always write as that number to the negative power. And that extends to other powers. 1 over 9 to the 4th is 9 to the minus 4. 9 to the minus 2 is 1 over 9 squared. 4 to the 7, I could rewrite as 1 over 4 to the minus 7, although I don't know why I would. And if I happen to have 1 over 5 to the minus 3, that I definitely think would make more sense to write it as 5 cubed. And so that's a quick recap of these 4 different rules of exponent. Let's move on, more rules. Let's look at 3 squared, and then I'm going to raise it to the 4th power. So again, exponents are repeated multiplication. So what I'm saying is I'm taking 3 times 3, and I'm raising it to the 4th power, which just means I'm doing repeated multiplication of the 3 times 3. Well, these extra parentheses are redundant, so I can just remove them and write all the 3's in a long row, all multiplied together, and I have 8 powers of 3. And 8 is exactly 2 times 4. So this rule is if an exponential is nested inside another exponential, you can multiply the powers. Let's look at 4 cubed raised to the 7th. That would be 4, and then you multiply the 3 times 7, which is 4 to the 21st. This is used a lot when you have something raised to a power, and then you have it to the -1. 2 times -1 is 5 to the -2, which is 1 over 5 squared. So often you'll start with something raised to a power, and then all of that raised to the -1, and that's another way of saying you're dividing by that 5 squared. Here's a x cubed to the -1 is 1 over x cubed. This is pretty flexible. It allows us to do nested exponentials. Now let's look at what happens if you are doing exponentials and they don't all have the same base. Exponentials with different bases. So for example, if I have 2 to the 7th times 3 to the 4th, I cannot add powers because they have different bases. That also goes for if I have something like 3 to the 5th times x squared, I can't add bases or add powers, can't add bases, can't combine them at all. But what I can do is if I have something like 4x cubed, we're going to use our rules of multiplication again. That's 4x times 4x times 4x. And when you multiply, it doesn't matter what multiplication you do the first. So I could just write this as a long chain of multiplications, and then I could move them around and put the 4's in the front and the x's after, and that becomes 4 cubed x cubed. So this rule, which is rule 6, you can distribute powers across multiplication and division, actually. So this 3 is being distributed to the 4 and also to the x. And it's convention when we do this to actually do the calculation on the number. 4 cubed is 64, but x cubed stays as a cubed. So you get to distribute the power 3 to the 4 and also to the x. Let me do a couple more examples. Let's look at, we're going to get a big one going here, 2xy squared, all raised to the 5th power. Well, rule 6 says I can distribute that power to each of the terms because they're multiplied. And then rule 5 lets me nest the powers with the y squared. So 2 to the 5th is 32. X to the 5th can't do anything new with that. And y squared to the 5th is y to the 2 times 5. So I get 32 x to the 5th, y to the 10th. So I hope one thing you're seeing is we often use more than one rule when we are rewriting things. Now let's look at x over 7 squared. So that you can distribute the 2 onto both the numerator and the denominator. And we get x squared over 49. Rule 6 says you can distribute powers across multiplication and also across division. And you can explore why that is if you want. You can rewrite this in a way so it looks just like multiplication, and then it all works out. Caution, and actually I'm going to go up here and I'm going to say caution, and I'm going to cross that out. And here's another caution. Exponents do not distribute across multiplication. Nope, sorry, across addition or subtraction. So the easiest way to show you that is just to give you a nice simple example. Let's do 1 plus 3, and we're going to square it. Now, according to PEMDAS, which is correct, I'll do the 1 plus 3 first, which is 4 squared, which is 16. But if I try to distribute the power 2 to both of them, I'd have 1 squared plus 3 squared. But 1 squared is 1, and 3 squared is 9, and that's 10. And that way is wrong. So you cannot distribute a squared across addition. You also cannot distribute it across subtraction. And maybe it makes sense with numbers, but where the problem often comes is when we use variables as well, because it's very common to see, oh, the squared goes on the x and the squared goes on the 3, but this is wrong. X plus 3 squared is x plus 3 times x plus 3. If I want to do x plus 3 times x plus 3, the way I do it, and I'm going to get into this a lot more later, but the way I do it is I draw a box, and I put one of my terms on top, and I put one of my terms down the side. Maybe I've already done this in this class, I can't remember. And I do the multiplication for all 4 pieces of this box. X times x is x squared. 3 times x is 3x. 3 times x again is another 3x, and 3 times 3 is 9. And then you add all the pieces up, and you get x squared plus 6x plus 9. That 6x is missing if I do it wrong. So squareds, any powers, they do not distribute across addition or subtraction. They only distribute across multiplication and division. Right, next rule, and I could explain this using the idea that exponentials are repeated multiplication, but the explanation is a little long, it's a little convoluted. So let me just say instead what the rule is. Roots can be written as powers. And will follow all the rules of exponentials. And this is really nice. A root is something like a square root of 16, which is the number you multiply by itself to equal 16, so that's 4. Or I could have the cubed root of 125. That's the number you multiply by itself 3 times to equal 125. And that's 5 because 5 times 5 times 5 equals 125. And here 4 times 4 equals 16. So these are roots, and you indicate the root with the number there. And if there's no number, it implies that it's the square root because it's the most common root. And we can write them as powers in such a way that they follow all the same rules of exponentials. Take the root and make it a fractional power. So the square root of 16, which remember when you don't see the symbol, we think of it as a 2. We take the root and we make it a fractional power, we make it 1/2. So the 2 in the root symbol becomes 1/2 in the power. If I have the cube root of 125, I can write that as 125 to the 1/3. I don't always put parentheses around the base, but sometimes it helps, especially with fractional powers. And as soon as we write roots using these fractional powers, they will follow all the other rules of exponentials. Here's a quick explanation on why roots look like powers. If I take the cube root of 125 and I multiply that number by itself 3 times, and then I write it in the exponential form, rule number 1 says I get to add these exponents. So it's 125 to the 1/3 plus 1/3 plus 1/3, which is 125 to the 1st. Which is 125. And that should make sense because the cube root of 125 is a number that you multiply by itself 3 times to get 125. And when I do that, sure enough, I get 125. So that's rule 7, is roots can be written as powers. And once you do that, you can do things like 3 to the 2/5 power. Well, that's 3 squared to the 1/5 power. This is rule number 5. This is our nested powers. And then I can use my rule 7 and rewrite that 1/5 power as a root. So 3 to the 2/5 is the same as the 5th root of 9. So just to make that a little more clear, it's not actually a separate rule, but when you raise a base to any fractional power, the denominator of the fraction is the root. So for example, if I do x to the 9/4, the denominator of the fraction is the root, so it becomes 4/4 root of x to the 9th. And I can work that the other way as well. If someone were to give me something like the 7th root of y cubed, the root number is the bottom of the fraction, and I get y to the 3/7. All right, these are all the rules of exponents that you need in order to write exponents in the most useful ways. So I'm just going to do a couple of examples. I'm going to write the following in a simplified form without any negative exponents. Often we're like, I don't want to work with negative exponents. So let's take 3x to the -2 y to the 4th and raise it all to the -5. So the first step I would use is I would distribute the power, because everything in here is multiplication. And I would get 3 to the -5 times x to the -2 raised to the -5 times y to the 4th raised to the -5. Three to the -5, I would probably write as 1/3 to the 5th. Because that -5 power, I can make it positive if I move it into the denominator. X to the -2 raised to the -5, I'm going to use the nested exponents, and that's x to the -2 times -5. And the same thing with the y to the 4 times -5. Let me simplify the arithmetic and the powers before I do anything else. -2 times -5 is 10, so that becomes x to the 10th. And 4 times -5 is -20, so that becomes y to the -20. I'm getting there. I don't have nested anymore. That's nice. So it's a simpler in general. I would say this is simpler. Since that number 3 is an actual number, I'm going to do that calculation, and you can use your calculator. That's fine. It's dividing by 243 because 3 to the 5th equals 243. And then I have an x to the 10th and a y to the -20, but I said I would write this without any negative exponents. So instead, I'm going to move it down and make it y to the 20 in the denominator. I started with the quantity 3x to the -2, y to the 4, raised all that to the -5. That's the exact same expression as x to the 10 divided by 243, y to the 20. Okay? I'll just do one more example and that'll wrap up the video. let's write the following without a fraction. 3x to the minus 2, y to the 3, z to the 4, divided by 7x to the 5th, y, z to the 4, all raised to the 2nd power. All right, in this case, there are a lot of ways to approach this. I could distribute the power like I did in the other one first. But in this case, I've got some simplification that I can do before I do anything else. So I'm actually going to use rule 2, where if you're dividing the same base, you can subtract the exponents. So the 3/7 can't do anything with that. But x to the minus 2 divided by x to the 5, I can write that as x to the minus 2 minus 5. And the y cubed divided by y, that may be more conventionally, I just cancel things out. Y cubed divided by y, cancel the y with one of them. And the z to the 4 over z to the 4, and this is a very common mistake, is to say, aha, no more powers, I just have a z. But that would be wrong, because z to the 4th over z to the 4th is 1. So the z's go away completely, leaving me just a 1. And now a little bit of simplification. 3 minus 2 minus 5 is x to the minus 7, y squared over 7, and then square all of that. At this point, I would probably distribute and get 3 squared times x to the minus 7 squared times y squared again squared. And remember that powers also distribute across division, so I also have a 7 squared in the bottom. And now I can do some simplification. I'm going to use my nested powers rule and just the numbers themselves. 3 squared is 9. X to the minus 7 raised to the 2nd power is minus 14, because negative 7 times 2 is 14. And then 2 times 2 is 4, so I get y to the 4th. And 7 squared is 49. And I'm really close, but I said I was going to write it without a fraction. So now I have to get a little bit creative here and say 9 times 49 to the minus 1 times x to the minus 14 times y to the 4th. And I've written this without a fraction. All right, that ends the video. Thanks for watching.